Okay, screen. All right, so we are now sharing. This is the second half of today. There it is. All right. Yeah, guys. Okay, so let's continue where we were. So we were just kind of give you some insight. We went to the repo I titled How LLMs Work. And I'm going through that right now. Essentially, this is part of the whole discussion on tensor operations. I remind you, um, there's a module here, tensor operations. It's not a homework, but you should go through all of these, code them up. They're very short little scripts, and they go from very basic stuff, like where we started today, that's problem 37. So there's 36 problems before that you should probably play with. Okay. All right, and then it builds up from there to the next thing. All right, so we are here in baby GPT and how LLMs work. So we were talking now about the attention mechanism. So we've discussed the dot product, we've discussed matrix multiplications, and now we are going to discuss attention. Right? I think the best way to understand this is to just do it mechanically. So we had started with a data set X. So that's this one here. Oh, yeah. So that's this one here, X32, comma 40, comma 512. I've already discussed this in the previous lecture. And now what we're going to do, what attention requires, is that we're going to do these transformations, essentially what we've been discussing. So I'm going to do that here. Which is going to be, this operation. If you notice, so I want to create a queue, right, which is just another variable. And notice it is quite simply taking that original X, matrix multiplied by a weights matrix, just like we did before, and adding this thing called a bias, which is another term, and transforming it. So it's exactly what we did before, right? But now we're going to do another transformation. And actually, we do that 3 times. So notice in every case, whether it's the Q case, the K case, or the V case, we're taking the original X and matrix multiplying it times a corresponding weights matrix. And we're just doing a transformation. So when we do the comparison, what's interesting here is when we do the comparison of X to itself, right, we're not directly comparing the X's. We're comparing the X's after they've been transformed. So we're actually comparing K and Q. And that just gives it, the attention mechanism more capacity. So it's less fixed on those words, and it can think in different ways, if you will. That's kind of the intuition. So, all right, so those are the ideas. So I don't need this now. All right, so we're going to go to back here. So that's the operation that I just did. So we want to compute the attention scores. And so these are the steps. So let me grab the code actually. So that one is just described there. Let's go to the all right, so let me find this. Probably this one. Yes, this one. All right, so we're going to start here. So attention converts X into K, Q, and V and performs the attention mechanism by matrix multiplication. So let's start here again. Okay, so notice I'm gonna set n to be 32. That's the number, the size of the batch. The sequence is 40, and each one of these tokens is 512. So we're gonna print the shape. So that's gonna be 32, comma 40, comma 512. Okay. So that's the X. But we just performed these transformations. So the first one is gonna be this Q1. Okay. So I'm going to do, so I create, just like before, a weights Q that is going to be N by 512 by 64. Because these are higher dimensional, you just have to keep in mind it's we're kind of thinking of the last layer always, right? So this is going to be N 512, 64. So this 512 maps to this 512, and then it's converting it to 64. Okay, so let's take a look. Okay, so notice this weight matrix is 32, comma 512, comma 64. We're going to add this bias here, which is going to be N4064 because it has to match like the size of the matrix that's coming out of here. Okay, so now we perform the matrix multiplication. So notice I'm multiplying X times WQ, right, to produce this value Q. So the first one, the first transformation. So what did we do? We actually went from 32, 45, 12 to 32, 40, 64. Do you guys see that? But you have to understand, it's like the same thing that we had before, right? So the batches, the sequence, the size 512, but in this case, we actually compressed it a little bit. Make sense? So why did we do that? Why did we make it 64? Because when they were creating the original transformer, they wanted to perform things in parallel, right? And they wanted to run this attention mechanism 8 times in parallel instead of just 1 time. So what did they do? They just said, okay, if we do this operation with 512 8 times, that's a lot of RAM. It's better to make it, you compress it a little bit, but actually run this 8 times, 8 different ways of, and you can think of it, I usually just think of it as it's 8 different ways of thinking about this problem. So then you're going to end up with 32 comma 4 comma 32 comma 40 comma 64, but you will have 8 of those. So if you take 64 times 8, what is that? Should be 512. So what happens is those 8 that are created at the end in parallel are actually concatenated to produce one final one again. All right, so that's essentially what's happening there. So if we go to the whiteboard, we can see that in the attention mechanism, we have an original X, which we will transform into K, Q, and V. Okay? But we also, this was originally 32, 40, 5, 12, right? And it was transformed into 32, 40, 64. Okay? Just compressed it a little bit, but that's because you're going to have times 8 of these, right? And then when you created 8 in parallel, Imagine this is one, this is the other one, dot, 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 all the way to 8. You're just going to concatenate them and create one single tensor of 32, 40, 512 again. Okay. Now, the reason why we initially in the attention mechanism, you can think of it as we're going to take X and we're going to compare it by itself, X. Okay. So we're going to compare X to X. But instead of directly comparing X to X, we transform into K and Q. Remember that each one of these will have its own set of weights. So it's like we have one additional step to look at the problem, right? So that now the real attention mechanism will happen between K and Q. It's still X comparing to X, but after they've been transformed by their respective weights matrices. Do you see that? So it's still the same. I mean, that's what's happening. So X is comparing to itself, but it's K and Q because they have gone through this matrix multiplication. And as I said, you just add this bias term at the end. That is also a set of learnable parameters. So that's it. That's the attention mechanism. But at the end of the day, if this has 40 tokens or whatever, then it's like 40 tokens just transformed a little bit more. Okay, and that's what we will see. So if I'm saying this, then that KQ matrix after that multiplication should be 40 by 40. And that's how you know. These are the shadows, if you will, that I was saying that allow you to tell if the operation has been done correctly. All right, so let's now go back to the code and let's take a look at it. All right, so here, as I said, I created my queue, and it is 32, 40, 64. Compressed only, actually, to save memory, because it's better to run 8 in parallel. So these are called the heads, and so the original transformer was called the encoder decoder with multi-head attention. Multi-head is this. All right, so I just did this part. Now I just add the bias, and we saw the bias, which is just over here, BQ. It was 32, 40, 64. This is 32, 64. This is very common, adding two tensors. So think of it like, if I add one grid of 28 by 28 with another grid of 28 by 28 to produce a new one of 28 by 28. All right, now take that out to a higher level by 1. Imagine you have a Rubik's Cube with values in each little square and another Rubik's Cube with values, and then you just add them exactly to produce a new Rubik's Cube with values. You guys know what a Rubik's Cube is, right? That thing that you do things like this. All right, so that's essentially what you're doing. That's going to happen quite a bit in transformers, adding those Rubik's Cubes. So now I have my first one, Q, done. It's ready. Okay, great. Now I do K. That's where that K, Q, and V, right? So this is K now, and I'm going to do the same thing. So I'm going to create the weight matrix. That's going to be N by 512 by 64. Remember, I picked the sizes so it produces the thing that I want, right? So remember, I wanted that weight matrix to be 4, 6 so that my output was 150, 6. So you got to play with these numbers until you get like the output that you want via the matrix multiplication. So now I'm going to do the weights matrix. Again, these weights are random and they're not going to be updated they're not going to be complete until training has happened. So that's why whenever you probably heard this, maybe, when you talk about large language models, they'll say Mistral 7 billion. What do you think that 7 billion means? It means 7 billion parameters, which means 7 billion weights and biases. And that's actually a small model. 7 billion barely runs on my Mac. or something like that. Actually, Mistral 7 billion is very big. But there's DeepSeek 650 billion. There's I'm sure, Mistral must have that, and who knows, OpenAI's is probably 1 trillion, right? Or more. Right. So those models are so big, in fact, they can't run on a laptop, right? They can only run on multiple GPUs. All right. So the more, and I don't mean in training, I mean in inference, like just running them in inference. But anyway, so that's why these models are so big. This is just weights that need to be learned. And you do that for K, for Q and V, and you do it for the embedding, and you do it for all these things, they really start to add up. And then you'll see there's actually multiple layers. But anyway, so we did K, we're doing K now. So again, I create the weights matrix. I'm going to create the bias just like before. All right, there it is, 30, 40, 64. And now I take X again. So I'm going to take X. And I'm going to perform a map mole. You can see torch.mapMole, the original X, right? The same X as before, times another set of weights to produce K. And now we've compressed it from 324512 to 324064. Again, so that we don't overuse RAM memory, and we're just going to concatenate these later. So you do 8 of them. All right. So now we add the bias. So that's going to be the final product, which is 32, 40, 64. That's K. So we've done Q and K, right? We have those two, Q and K, and now it's where you do the attention mechanism, right? And like I said, remember, I've simplified this. So I've removed a few functions that like a softmax, etc. But now we do this operation. So the attention mechanism, I would describe it as this. This is the attention mechanism. So this K times Q, which should produce a matrix that is N 40 by 40, which intuitively you can imagine as, the cat is sleeping on the chair, the cat is sleeping on the chair, and you're just comparing, like, how does it relate? But let's do the operation first. Here I'm going to do like that. So this is the attention scores, a torch.mapMole, but this time, notice it's not like X and weights. This time it is actually Q, mapMole, K, and notice that I'm using this function called transpose just so that it's aligned properly. All right, so this is important to align it properly. And when I run this, guess what? 32, 40 by 40. Do you guys see this? So why is this important? So now let's go back to the whiteboard, right? Right. So I was doing this. The intuition is that I have X to X, right? So it should be the sentence is 40. So then it's 40 here and 40 here. But I transform the X into K and Q, but it's essentially the same dimensions. So the output is 40 by 40. So now we can imagine this as being, I'll use the example. The bank robbed today. You see that? And then this one, the bank was robbed today. This is kind of what's happening. Just remember, it's actually embeddings, not integers, right, that are in there. And so you have to think about all of those things. But you can imagine how one embedding can be compared to another embedding to produce a what? A single value. How do we do that? A dot product. So remember how I did a dot product that was 4 dot product 4? Do you remember I did that at the very beginning, right? To produce a value. Well, one way of intuitively thinking about this is to compare two words. Well, I know that bank is a vector, but not of 4, right? It's a vector of what? 512. Do you agree? And then another word, such as today, for instance, is also 512. So if I do a dot product of these, what will I get? One value, if you remember, right? I would get just one single number. So obviously I can do an operation such as this. So it's like you give the LLM operations, but then it's going to figure out, because it's going to do one and it's like 32, and that's not useful. But then it does another one of the two, and that one is 117, and that one is useful. If you think about it that way, because those are weights that are being processed. So now, and essentially that's the mechanism, but intuitively, what are you getting? Well, what the large language model needs to understand what it's looking at, right? It needs to understand. So it needs to understand that, it's an LLM and it just needs to answer a question or whatever it is and know the context. So you can imagine that bank and today, right? Yeah, it's important because that's more important than saying bank and wormhole, right? Like, how are those two related? But bank and today, okay, there's more, that one's a place, one's a location. But for any problem that I'm trying to understand about bank, so this value, let's say, just for the sake of argument, I'm going to say that this is 3. But bank and Rob, that's really important to understand what the meaning of the word bank is. So this might be something like 55. Do you guys see that? So that's essentially the intuition of the attention mechanism. That it's trying to find, it pays attention to words that are important. And this is happening during inference time. So it's going to happen during training that you learn the weights, but during inference time, you ask it a question like, what happened to the bank today? Okay, the bank today, right? And it's going to trigger these things, and it's going to know that you're talking about the financial institution and not the river or whatever it is. But we just give it, you have to agree that by doing that operation that I showed you in PyTorch, I'm able to create a machine that creates these 40 by 40 matrices. And what they're doing is they're comparing the members, like the individual words. Then the training will fill in these values. So remember, right now, all these values are random, but during training, they will be filled up. How? Like bank and robbed. That's really important. That tells me, okay, that this is more related. The vector that I need is one vector that is related with the financial institution, not something. Any questions, guys? That's like the key intuition there. No questions? All right, so that's the attention mechanism. It is 40 by 40. All right, so now I'm going to go back to the code. And just to kind of finish up that idea. All right, so I have 32 by 40. So essentially I built that. That's really great. I've captured my attention. When I do the training, I have awesome weights that work really well. What do we do next? Well, we need to come back to 32 by 40 by 512 because that's actually the tensor that is moving through the neural net. And so that's where the V comes in. So if you look now, I'm going to do the V1, and it's essentially the same as K and Q. So I'm going to grab WV. All right, so this is N by 512 by 64. Okay, so I did that. So that's the weight matrix. Then I'm going to calculate the bias. Okay, so that's the bias. Same thing. And now I perform a matrix multiplication. All right. So X, again, remember, is the original X with its corresponding weight matrix to produce a 32 by 40 by 64. Okay. So I do that. And then I just add them to produce a V. This is similar to everything we've done with K and Q. So now it's 32 by 40 by 6. Oh. Turned off. All right, so here we are. So again, we just transformed that original X, right, to be 32 by 40 by 64, similar to K and Q. All right, so we run it. And now we perform a matrix multiplication, but notice what we're doing. So it's a transformation of the attention scores. So the matrix that is 40 by 40, now we're going to multiply it times V so that we can get back to our shape 3240 by 64. Do you see how that works? It's like they just like stumbled on this concept of, hey, if we do matrix multiplications, we can mess around with the shapes of this thing, right? And as long as we keep some things consistent, like 32 and 40, right, which has meaning like batches, you can't like mix that with anything else. Batches are batches, and the sequence, the rest we can play with. And so then we build this architecture from beginning to end of all these transformations, and then we just train it with massive amounts of data, and it'll learn. And it did in a very surprising way. You see that? So transformers are this. It's just take that matrix, and if you can imagine some set of weight, some shape, and the dimensions work, do it. And then keep doing that, and then eventually come back to the n by 40 sequence, because you're going to train it with all the internet. Essentially, it'll pick up something if it's good. All right. So now we've done 32 by 40 by 64. And so that's it. I have now done the attention mechanism on my data, on my X, right? But what I had, remember, I compressed them to be 64 because I wanted to do this 8 times. They decided doing this 8 times is better. Doing this 8 times with something smaller is better than just doing it once with something big. So this was like a trade-off, especially in 2017. This is still done today, but the dimensions can be increased a little bit. So here I'm only simulating this part, but essentially I'm gonna do this like this, which should be consistent. I'm going to imagine, that whole process, X, Q, K, V, I did all of that. What I get is this product 32, 40, 64, right? So that is, I called it out. Do you see that? So that matrix out is 32 by 40 by 64. What I'm gonna do now, and this is I'm just gonna create a list of 8 of these. So that's all I'm doing. So I'm instantiating, it's like I'm instantiating that 8 times. So I have 8 heads that are 32 by 40 by 64. And you can see I'm going to print these out to confirm that. So now I'm going to iterate through the list and print the shape of each one. And you can see I have, in fact, 8 matrices that are 32 by 40 by 64. It was the original same X, but just done 8 times. And the best way that I can describe this is I take 8 of you and I give you the same problem and I let you go for a little bit. Then you come back, all 8 of you, and all 8 of you maybe thought about it a little bit differently, something like that. And then I take all your ideas into one thing. But I don't actually like summarize it. I don't average it. I don't summarize it. Instead, I just I put all your heads together and concatenate them into a single thing. So all your data is not summarized, it stays. And that's what this concatenation part is here. So if you notice now, I take the list heads of all the 8 and I concatenate it on the last dimension, the 64, and 64 times 8 should be 512. So essentially, I arrive back at the original thing that went into the model. And that's another thing that's really great, I think, about the way that transformers were made. Sometimes these things are like, how did they know that? How did they know to do that, right? That's kind of how you, but essentially they had the goal, the Google people, they have the goal of doing certain things. They wanted to do attention, they wanted to do the embeddings, they wanted to do a couple of these things, but other things they wanted to simplify. And one of the things that they simplified is that a transformer, you have a tensor that is batch or whatever by 40, the sequence, whatever that is, by 512. It goes into a pretty complex layer that has attention, it has feed forward, whatever it is. But what comes out of the layer, regardless of how complicated it is, guess what? It's gotta be 32 by 40 by 512. Because what they wanted to do is then they would say, okay, I built this layer. I want to do that now 6 times or 32 times. Do you see that? And so essentially, they needed to have something, the thing that came out or went in and came out was always the same tensor, 32 by 40 by 512. And then you go from input all the way to the end of the end here of the model to be 32 by 40 by 512 until you finally maybe map this one to the word, because at the end of the day, here we have to come back to the word itself, or the subword as it's called. So yeah, so that's why that's a pretty nice thing to when you're thinking about transformers. The tensor goes in like this and it comes out like that, regardless of any kind of jumbling or things that are happening inside. So let me do. So, we did all these crazy things, compressing them, creating 8 of them, but then we concatenate them and it comes out as 32, 40 by 10. All right. All right. So now that I've done this part, that's essentially the attention mechanism. So that's almost all of it, which is kind of the hardest part. So and then there's a few other layers, like there's going to be a projection layer. So this is actually a nice exercise. So this one says another projection for the concatenated 8 heads. So let's think about this one a little bit. And this we can cover later. Then we have to do token embeddings, of course. Positional embedding has to happen. So that's also. So yeah, there's a few things we have left, but let's do this part next. So I have a tensor that is 32 by 40 by 512. What do they decide to do? You know what? Let's take that 512 and make it bigger for a little bit. Learn some weights, and then take that bigger thing and make it 512 again, and learn some weights in that process. And you can think of it as just giving it more capacity. Okay? So here I'm going to create yet another weight matrix. Notice that. The theme today has been these weight matrices and matrix multiplication, right? So I create another weight matrix towards random. It's gonna be n. Notice, because it's the 512, this is only 512, my output cat, right? And then I'm just gonna map it to some higher space. So let's do this. We use 0. Now I'm going to, do the bias. Okay. And I'm going to now perform a matrix multiplication. So this output cat, remember, is 32 by 40 by 512. I do the matrix multiplication. That comes out as 32 by 40 by 512. But I can, choose a different size for it. So this one is 32 by 40 by 20. Oh, I did 2028, but I meant 2048. It's got to be correct. 2048. Why did I do that? Well, first of all, because I can. That's what like Google's thinking. I can do that. Hey, let's do it one more time. Why intuitively? Maybe again, just to give it some more capacity to think about. Because remember that set of weights also has to be learned. So maybe that helps to project that. Remember, you're projecting to a higher dimensional space, so maybe that helps. And then you reduce it back to the 512 again. Okay? So that's essentially, this usually happens at some point after the 8 blocks, you do this operation. Okay? And then you add the bias and so on. So I'm going to save the part of the mask for a little bit later. All right, that's probably one of the last things we'll cover. But the mask is a pretty important concept. So I'll go through this a little bit later. Yeah, so this is all masking. And now I want to talk a little bit about embeddings. So I'm going to go back to this idea of token embedding. So this is the idea of the 512, if you remember. So this might be something pretty interesting. That's at the beginning. So token embedding and actually positional and token embedding and how that works. And actually, I think that's the last of it. So I think if we cover this and we cover the masks, then we should be ready to do the full little baby GPT. So let's try this one out. So token embedding. So token embeddings means going from ID 17 for cat to vector 512. Okay. So that's what that means. So I'm doing token embeddings here. Okay. So let's just think about it a little bit. I'm going to use some parameters. So here I'm limiting the vocabulary size. I need to have a vocabulary size. I think I told you guys that it might surprise you, but something like GPT-3, I think I read, is about 50,000 tokens, actually, subwords. Here I'm just using 1,000 for the sake of simplicity. The embedding size is going to be the same embedding size we have been using, 512. I'm going to assume a sequence of 10, so that's like 10 words in a sentence, and a batch of two samples. Okay. So I have this here. So I'm going to create the tokens. So I'm just going to use random ints, which means I'm going to use, simulate some token IDs, right? The vocabulary goes from 0 to 1,000, right? And then it's going to be the sequence 2 comma 10. Okay. So if I look at the shape of this, and we're going to look at the shape and the values. All right, so this is the shape, 2 comma 10. What does that mean? There's two sentences, and each sentence has 10 words. Do you guys see that? Make sense? All right. So that's what I did. Now, if we look at the actual tokens, you can see now why I selected such small values, right? The whole point is that we're able to visualize it. So these are just random still, but they are now random integers. So this is essentially how you would get your data. You would get 32 sentences with integers and sequences of about 40 integers. And those are coming from the actual subwords in the text itself. Okay. So now, what do? We're going to create, remember I told you guys that there was this embedding layer, right? So there was this embedding layer. And this is the one. So Torch has this library, or this, sorry, not library. In the library, it has this construct called NN embedding. So I'm gonna, invoke it from Torch NN. So from Torch NN as NN, I'm going to define the embedding layer. This is literally how you code this with PyTorch in the GPT or the LLM, whatever it is. This is the actual tool that you use. This embedding just think of it as a two-dimensional matrix of rows equal to the vocabulary size, so that's 1,000, and then columns equal to the embedding size, so that's going to be 512. Okay, so we create this object as a layer. Okay, and then once it's created, we run the data through it. So notice here, we want to get the embedding vectors. So notice I'm giving it this, which is the two sentences with its values as integers. I'm going to run it through this embedding layer by tokens, which is this one, right? I run it through this embedding layer, which is this one, okay? And now notice that I produce 2 comma 10 comma 512. So I've added in, that additional dimension that for each ID, I have a vector for use. Does this make sense, guys? Any questions? So this is yet another portion of this, right? So we're almost there. So now what you need is a way to go from strings, like the actual words, to the integers. But once you can do that, then you can use this code to go from the integers to the 10 by 512, right? So this is the same as 32 by 40 by 512. So let's imagine that we created this randomly, right? So sequence now, I'm going to change it to 40. Batch size, I'm going to change it to 32. Okay. 512 has always been 512. So I'm going to create this tokens that's been created. I'm going to run this shape. You can see it's 32 by 40. I'm not going to print it because, it's like a lot of data. And now I just run this through the embedding. There you go, 32, 40, 512. And now this is exactly consistent with everything I've been doing, with the attention and everything else. That's it. This is the magic of all of us. And this is just, this one is an actual object embedding, but it's doing that the same idea. All right. So we've done this part. So now comes positional encoding and token embedding. This one might be a little bit tricky. This is probably one of the things that took me the longest time to really grasp positional encoding. So let's talk about it a little bit. I'm going to switch to the whiteboard. All right. So let's think about it a little bit. So what is positional encoding essentially? Would you agree that it's important to say the car was going fast and then it question mark, right? So this sequence is really important, right? To know which word came first. Because I could say the fast car was going slowly. Do you agree with that? So you can see how I can change, if I change the order of the words, what's happening there? The meaning of it is changing, right? Do you guys see that? And so it's really important to have positional information about the sentence as well. And so far, we haven't done anything about position. We've only looked at tokens, right? And the embeddings and all of that, but we haven't actually, we want to know that in this sentence, this one is, well, let's say 2. Here is like 1, 2, 3, 4, 5. In some, with respect in particular to car, where car is like 2 here and here's 3. So, all this context is really important. So when we convert these sentences into actual data through embedding, we also want to capture something about the position. And what's amazing about this is that we use the exact same trick that we used for the previous one. Let me give you an idea. So, we have a sentence, right? We've agreed, and the sentence is 17, 55, 2000, 703 for whatever reason, right? So we've already established that these are these IDs in the vocabulary to 512. Okay? So now I need the positional encoding, whereas it turns out, what I can do is create an equal, like vector, just like this previous one. But instead of having the IDs representing the actual words, I just do this. Do you see that? So I just put, actually, instead of the IDs, here the numbers are just the sequence itself. Why is this useful? Because here I was mapping the IDs to 512. Here I'm going to map what? 1, 2, 3, 4 to an embedding of 512. Do you see that? So what does this mean? For every one of these positions where I have an embedding of 512 that has the meaning of the word, I also have an embedding of 512 that has information about what? The position itself. Because I'm going to say this was position, this word 55, this word 55 is position 2. So it's going to have a vector corresponding to the word itself here and a vector corresponding to position 2 here. And they're both the same size. So what that allows me to actually to add them together, right? So that's essentially what you're going to see me do. And this is how one of the two ways in which positional encoding gets done. The other one is using this idea of sines and cosines, but I always like this one better. And the only key thing is, remember, you only define the shape, so these values still need to be learned. So just like these values are learned here, the positional values are also learned here. Does that make sense, guys? Are there any questions? This was I won't deny that this is one of the parts of this that took me a second to understand. It's kind of, again, how did they know to do that? Do you see what I'm saying? All right, so let's try it out because this is going to be really important, as you will see, when we're feeding data into the actual architecture. We're going to take the data and the positional data, add them up together, and that's what goes in. So let's go back to the code and kind of think about this again for a second. All right. So I'm going to do here. So I did the embedding first, right? That hopefully that made sense. Now I'm going to do positional and token embedding together. So let's copy these parameters. All right. So once again, 1000 is the size of the vocabulary. Embedding dimension now 64 instead of 512. Right. Let's use that just as another example. Sequence length 10, and batch size is just 2 to keep it small. All right. So I'm going to go ahead and do that. So here's the tokens. Just like I did before, I'm just repeating. So same idea, random integers, but I've gotten this through some tick token, so where every word is mapped to an ID. Okay, we saw them, I think. Then I do the embedding. Okay, so that's going to be, again, vocab size to embedding dimension. That's the token embedding. That's just like the layer. And then I did that. So that's token embedding. No. Just give me a sec. So these should be the random int. I created the token embedding. I've done the token shape actually. So it's this part here. And then we'll do right. So I define token embedding as 1000 by 64. And then I run the actual tokens through it. And I get 2, 10, 64. That's just the data. Currently just the words, the whole embedding idea. Now it's like we repeat that whole entire idea, but for sequence. So the trick is, instead of these IDs, now it's just the sequence order. All right, so I'm going to do that here. I need to create the object, so I'm going to create the object here. Okay, so notice this is not token embedding anymore, it's position embedding, but it's the same NN embedding, and it goes from sequence length to embedding dimension. Why sequence length? Because now it's position 1, 2, 3, all the way to 40 or 10. I want to know where in the sentence they are. So it's almost fixed in a way, right? So it's that. So I create positional embedding. Okay. And I did token embedding here. So now here is like the magic. Take a look at this. Where before, my two sentences look like this for the actual token they are. Now they look like that, right? So if I run this, notice what it is. 0, 1, 2, 3, 4. It's just a position. And then for each one of these IDs, 5, I'm going to get an embedding of 512. And the neural network then has to learn what being a 5 in a sentence means versus being a 1 or being a 9. And then that's always added to the, but also in a meaningful way, so that when I add that 512 of position to 512 of like the context, that they both provide enough information, right? Because it's really important to know where the sentence, where the word is in the sentence. Okay, so that's it. This is all positional encoding in a transformer that you give it. So now let's, so with that shape is 2 by 10, so you guys can see that. All right, adding more cells here. All right, and now here comes the positional embedding. So notice we invoke positional embedding, which is this one, the NN embedding. We run the positions through it, and now the tensor is 2 by 10 by 64. The other one, the token embedding was 2 by 10 by 64. This one is also 2 by 10 by 64. And then all they do is add them together to produce a new tensor that is 2 by 10 by 64. And remarkably, this works. But actually, there was evidence that this works because there's something called residuals. And residuals are kind of this, the way that they solve very deep neural networks. And it was the idea that you had an X, you ran it through the function, and that's how we would do things in the past, right? X through the function, and then that goes into the next one. But the problem is when you were doing that in a very deep neural network, you were multiplying very small numbers together. So it's like the example, if I do 0.5 times 0.5, what is that equal to? 0.5 times 0.5. 0.25. And then if I do 0.25 times 0.25, what is that equal to? Even smaller, right? And it just keeps getting smaller. So that was called the vanishing gradients problem. And so essentially, eventually, after a very deep neural network, those values were essentially 0. And so you had no meaning. And the solution to that was to simply do, so the solution to that was to simply do, whoops. So I was saying, so you're doing, 0.5 times 0.5 equal 0.25, and then 0.25 times 0.25, and what was the value someone said? 0.6, what is it? 0.25 times 0.25 should be a smaller number, right? Oh, 0 point. Okay, like this, right? Yeah, and this is smaller, right? So it's getting smaller, but that's because we would get an X, run it through an FX, right? And that would become like Y. And then this Y would run through another F1 and become H or something. So it was always being transformed. And the solution with residuals was to simply add the X. And then here add the Y. And you were just adding them together. And just that alone solved the vanishing gradients problem. Obviously, to add two things together that are tensors, they need to have the same dimensions. Do you see that? Otherwise, they're not going to add together. So this solution was not actually far-fetched. It's the solution that solved residuals. So then now they're just like, okay, well, I have my sentences, my embeddings, which are 32 by 40 by 512. I'm just going to create another tensor, 32 batches, 40 by 512, that captures this information of sequence, right? And then you just add them together. Okay, and so that's essentially what happened there. So to produce another one that is n by 40 by 512. So if you look here, you can see I have I'm using 210 by 64. So I'm going to switch this to n by 40 by 512. So it should be 512 here. I'm going to make this 40. Batch size 32. Okay. So I can be consistent. I can generate the tokens, but just not print them because it's going to be a lot. Right? So I have my, one way to corroborate tokens.shape, 32 by 40. Great. The embedding now, vocab size, that's still 1,000. Embedding size is 512, and then I just run it. And it's 32 by 40 by 512. That's just a normal embedding. We talked about that already, right? Discussed that at length. But positional encoding, amazingly, is just that, right? So, but sequence length instead. So the 40. And embedding dimension is 512. So I do that. The trick is, again, maybe just do like 1. All right. And so I do this. And there you can see it's 0, 1, 2, 3, essentially just a position from 0 to 39. Do you see that? But you create an embedding for it. Okay, 32 by 40, right? For your values but only not looking at the ID itself, just a position. And then now you do the embedding, and guess what? It's 32 by 40 by 512. So you just add them. And that's what we're going to see here. The last part of this is that, and this is how the GPT works. You add the token embeddings and the positional embeddings, which have the same dimensions, to produce the final tensor, x.shape, which is 32 by 40 by 512. The key thing to think about here is that the weights are helping you. You see that you do these operations, but during training, the weights are updated in a way that the system meets its final objectives. So that's kind of the help, but that's essentially how it works. Yeah, questions? Nope. All right, so yeah. If this is still a little abstract, that's fine. Like I said, actually, certain things made more sense to me when I was thinking about LLMs, when I was learning about them. This part took me a while for some reason to see that such a simple trick would capture the positional encoding. All right. All right. So it's 7:38. This class ends at 7:50, right? 7:50. Yeah. All right. So let's just see what we have left. Okay. We've basically gone over all the parts. And so really what comes in now is to kind of build this thing together, right? And there is the masking part, which I'm saving that for the next time because, yeah, that one's probably the hardest to visualize. So we need to do that with an example and take enough time. But let's just look at our notes. My suggestion, if you understood this 100% today, wow, great. Good, good for you. Otherwise, go over the code. Play with the shapes. Think about this. There will be a lot of reading later, but I feel like what's the point of reading a paper or reading some notes if you have no idea what that operation is doing. You know what I mean? So you got to have some intuition. But let's take a look at where we are, right? So this is my linear algebra attention mechanism. So we've covered positional encoding or embedding, token embedding. We didn't cover the masks yet, as that is less trivial. So we have to spend a little bit of time on that, but that doesn't hurt your understanding of the rest. Something that we can like add on later. We did the additional projection, so that has been done. We concatenated all 8 heads. I showed you the attention mechanism, QKV, queries, values, and keys. And mechanically, that's exactly how it works. So now let's take a look over here. We went over these notes, I believe. So we went over attention. So this is what I just discussed. The softmax, like I said, I did take out a few functions here and there that I will add back later, okay? Because I think those don't break the flow of understanding. Simulate multi-head, I did all that. By the way, this is the paper. Attention is all you need. You can read it now, right? It's great. And on the more you understand all these operations, the more it makes sense. But this is, I would recommend start reading through these, right? This is like one of the most important papers in computing of all time, right? It's probably one of the top 10 or something like that. So definitely read it. And then we have the baby transformer itself, whereas you can see I'm putting together all the code from beginning to end. So what I'll do today is I'll just kind of talk about it so that I don't rush it, and mention, okay, we cover this, we cover this, we cover that. And then later next week, we will come back to it. All right. So let me just go to, that's essentially this README, right? So that would conclude it. Yeah. So now let's just take a look at the code examples that we did, just to kind of put them into context also. So, and in linear, this is the first thing we started with. That's the dot product, the whole thing we did with Iris, right? So we've covered that one. So that, that's the image. This is the one I just did. This is just, as I said, the actual book, Huckleberry Finn from the Gutenberg library. This is GPT background. So this I think, this is tick token. I have not covered tick token. So tick token is when you want to go from actual text like Huck Finn to the integers. All right. I have not done that part. I think it's a bit, I don't think we have enough time for that today. So we'll do this next time. Okay. Or you can read it on your own, but I'm going to save it for next. Remind me, but I'm going to try to save it for next time. This, as I said, GPT from scratch. So hopefully now, if you start reading this code, which is the actual GPT full on that you will use for your project, you can start to identify certain things. Like if you look at, let's see, you look at, this is a head, right? So if you look at this, guess what? You have a Q times K, right? You know that this is K and Q, right? So that starts to make a little bit more sense, except that remember that I said, whereas I was defining the weights, the biases, when we define our K and our Q, it's going to be a lot easier because we're going to use NN linear. Does that make sense? So that's just going to make it way easier for us. But that's essentially the attention mechanism with things added back. Notice this. This is that projection that I did from 512 to 2048 and back down. That's what this is. So now you have a little bit more sense of it. These are the 8 heads. You see, remember I did 8 heads that I concatenated later? That's them. Notice here I have a torch cat. I'm literally concatenating the actual heads. So a lot of this that I broke down into parts is actually in the code. This is kind of like the blocks. So you'll see that actually I'm only doing one block, but the actual transformer is a sequence of 6 blocks. And there's a few tricks there. So we'll cover that. And then that's it. This is the class that brings everything together. For instance, notice that IDX is what I've been calling X all day. And then notice what I do here. This is the token embedding, the thing we just did. This is the positional embedding. And notice here, we just add them together. Token embeddings plus positional embeddings. The example I just did, but now in the corresponding part of the code. And that is it. Okay. After that, what comes is just instantiating the model. This is the training process, the losses. If you've ever seen any neural network, you'll see that this is exactly like you train any other neural network. So we'll, of course, dive into all these. Today is just essentially the operations, okay? Don't expect to understand, if you feel like terrified, right? Don't expect to understand an LLM today because we're not even describing an LLM. We're only describing the tensor operations, the matrix multiplications that underlie the whole thing, right? Yeah, so this is the full-on LLM. And then we have 5 minutes. So the last thing I have here probably is the baby transformer, which is this one, which we will run in the next class. But I just want to show you it should essentially be the same parts, right? So let's just take a look at it. Super simple, the most simplified. I can make this, I think, but I did try to make it from beginning to end without training. So it should go from integers to the vocabulary tensor. So you can see here I'm being consistent. These are the tokens. This looks like the tokens that I did. Then I do embeddings and positional embeddings here, and I add them together, as you can see here. So that gives me 2 by 10 by 64 consistently. That's what I do here. KQV, right? That's the attention mechanism. So I define them, but I'm using NN linear. Notice that X here is token plus positional embeddings. And that X then just goes directly into my KQV. Do you guys see that? Which is exactly what we did. We print out the shape here of one of them. And then what's this one? This is the same as before, except that you will notice that now there's 2 lines of code because now it's got everything, right? The things that I took out for simplicity, we're going to start adding them back. What is a softmax? Why is that necessary? It's actually quite meaningful why that's in there, but we have to take our time. And it ties into the mask also. So, it's a little bit tough. All right. And then once we have the attention scores, we multiply them times V, just like we discussed, right? And that gives you your attention output. And then, so that's attention output here. And then we will have defining these forward layers. And notice that these forward layers just take attention. You run it through an FF, the first forward layer, then a ReLU, then another FF2. If you've ever seen PyTorch, this is essentially the classic layer, okay? Which we will do some simpler examples as we dive into all these things, but just giving you that. So here, the attention goes in here through just some normal feed-forward layers, all right? And then we produce, and then here comes the trick. We create, notice here, the final projection to vocab. So what we do here is this projection goes, if you notice, from 512 to what? Vocab size. So it goes now finally to the words, to 1,000 or 50,000. So you can see that the final tensor that comes out of the neural network is what? 2 by 10 by 1,000. So in this case, now it would have the ID 17, 55, we had a lookup table. What was 17? I've been using 17 a lot for cat. So then you would get the word cat. Make sense? All right, so take a look at this one. This is like the baby GPT. We will come back to this one. We'll start here next week. All right, and just go through it, kind of review everything that we've done. And and then of course, at some point, look at the actual LLM. All right. So again, my suggestion as far as homework, you can, I'll end here.